Hey everyone, welcome. Today we're going to tackle a topic in calculus that can be a major headache, solving those initial value problems. But what if I told you there was a powerful shortcut? A simple three-step method that can turn really tricky calculus into, believe it or not, straightforward algebra. Let's dive right in and see how it works. So, does this sound painfully familiar? You grind through all the hard work to find the general solution to a differential equation. You think you're finally done, but nope. Then you have to go back and solve this whole system of equations just to find your constants, C1 and C2. It's such a common pain point, but I promise, there is a much, much more elegant way. The traditional methods, they work. Of course they do. But they often feel like you're taking the long, winding, scenic route when there's a direct highway just waiting for you. They can be pretty clunky, and honestly, every extra step is just another chance for a tiny calculation error to sneak in and mess everything up. And this is especially true when things start to get complicated. I'm talking about messy forcing functions, or even worse, piecewise functions, which, if you're in engineering or physics, you know are everywhere. With those, the traditional methods can really start to fall apart. We just need a better tool for the job. And that tool, our absolute hero for today, is the Laplace transform. Seriously, for these kinds of initial value problems, it is a total game changer. So, what is this thing exactly? Well, the formal definition says it's an integral transform. It takes a function in what we call the time domain, f of t, and it converts it into a totally new function in the frequency domain, which we call f of s. But here's a much simpler way to think about it. The Laplace transform is basically like a universal translator. It takes a really difficult calculus problem and translates it into a much, much easier algebra problem. I mean, look at the comparison here. Instead of finding those constants at the very end, this method just bakes the initial conditions right in from the start. It makes the whole process so much cleaner and more direct. So, let's get right to the core of it. This isn't some complicated 10-step process. It's a simple, repeatable, 3-step program that you can apply every single time. And the workflow is always the same. It's beautiful. First, you transform the entire differential equation from the time world into the s domain. Second, you just use basic algebra to solve for that new function, y of s. And finally, you take the inverse transform to bring your answer back into the time world. That's it. Transform, solve, inverse. That is the entire process. All right, talk is cheap, right? Let's actually see this thing work. We're going to walk through 3 examples pulled straight from the study guide to show you just how powerful and crazy efficient this technique really is. We'll start off with a pretty straightforward first-order equation, y prime minus y equals 1. And the initial condition is y of 0 is 0. This is the perfect first case just to see the mechanics in action. And here it is, the whole process laid out. Okay, step 1, transform. The derivative y prime becomes sy minus y of 0, which we know is just 0, so that's easy. The constant 1 becomes 1 over s. Step 2, solve. A little bit of factoring, a little bit of division, and we get y of s equals 1 over s times s minus 1. Now for step 3, inverse. To get this back to the time world, we need to use a little trick called partial fraction decomposition. It lets us split that fraction into 2 simpler pieces. Once we do that, we can just look up each piece on our transform table and bam, we get the final answer, y of t equals negative 1 plus e to the t. And notice, no messing around with constants at the end. Okay, let's ramp up the difficulty a bit. Here's a second-order equation with a much nastier function on the right-hand side. And we've got 2 initial conditions this time. Now, with the old method, this is exactly where things would start to get really, really messy. And this problem just beautifully illustrates the single biggest advantage of the Laplace method. Those initial conditions, y of 0 is 2 and y prime of 0 is 6, they aren't some afterthought you deal with later. They get incorporated directly into the very first transform step, and it simplifies the entire workflow. So after we transform both sides and group all the y of s terms together, the algebra step is just to isolate y of s. Now, what's really cool here is how the terms that came from our initial conditions, that negative 2s plus 6 from the previous step, well, they can be factored. And this allows for this just beautiful cancellation when we divide, leading us directly to this much simpler expression for y of s. And from there, it's pretty much downhill. We just take the inverse transform of each piece separately. That first term gives us 2e to the 3t. The second term, it perfectly matches the standard transform formula for t to the nth power times an exponential. And just like that, we have our complete final answer. Done. All right, for our last example, let's look at a true classic from physics, an undamped harmonic oscillator. This is the equation that describes things like a simple pendulum or a mass bouncing on a spring. So we're starting from rest at the origin, but we're giving it an initial kick, an initial velocity of 10. So let's transform it. The y double prime becomes s squared y of s minus s times y of 0 minus y prime of 0. Now we just plug in what we know. Since y of 0 is 0, that whole s times y of 0 term just vanishes. Nice. Y prime of 0 is 10, so we have a minus 10. We move that to the other side of the equation, do a little factoring and dividing, and we land right here. Y of s equals 10 over s squared plus 4. Now for the inverse transform. This is a neat little bit of algebra. We need our expression to match a standard form from our Laplace table. We know the transform for sine of kt is k over s squared plus k squared. Well, in our problem, k squared is 4, which means k has to be 2. So we need a 2 up in the numerator, but we have a 10. So what do? The trick is to cleverly rewrite 10 as 5 times 2. Now that 2 over s squared plus 4 part is a perfect match for our sine pattern. And that number 5 that we just factored out, it's not just some random coefficient. In the physics of our problem, it's the amplitude of the sine wave we're about to get. How cool is that? We found a key physical property of the system just by doing the math. This gives us our final answer. Y of t equals 5 times the sine of 2t. So after seeing it in action, hopefully you can really appreciate why this method is so powerful. It's not just another trick to memorize. It's a fundamental shift in how you can approach these kinds of problems. So let's just recap the huge takeaways here. The Laplace transform gives you this one, single, unified system that turns calculus into algebra. It handles your initial conditions right from the very beginning, and it makes even really complex problems so much more manageable. It really is a superpower for your mathematical toolkit. And that kind of leaves us with a final thought. The big idea today was transforming a problem into a different world where it's way easier to solve. So the question I want to leave you with is this. What other problems, maybe not even in math, could be cracked if you just found the right way to change your perspective?